Good morning. Today we will dive into the fascinating case study in computer architecture, the adaptive epiphany processor. Our focus is not on the peak speed, but on the radical design choices the company made to achieve industry-leading power efficiency and scalability. Key points to emphasize. The epiphany represents a major architectural divergence from mainstream CPUs, prioritizing parallel throughputs over single core speed. Now, coming to architecture overview, first we will come to key design principles. Its key design principle is it's defined by three things. It's many core, mimid, and RISC architecture. Unlike your standard dual core or quad core CPUs, this chip scales massively, featuring up to 1024 simple custom RSC cores. Its philosophy is simple: use many high efficiency workers instead of a few complex ones. The target applications, we can say, this design specifically targets embedded systems and real-time processing, such as autonomous drones and complex radar systems, where power is the most critical constraint. Now coming to the ISA part, the instruction set architecture. So the ISA reflects a chip minimalistic philosophy. It's highly compressed 16 to 32 bits instruction, which saves on instruction fetching and memory storage. A direct win for energy efficiency. The register is simple, 64 registers keeping core complexity low. Crucially, the ISA is optimized for floating point math. This makes it an ideal math coprocessor. It doesn't need all the complexity of a general purpose instruction set because its jobs is highly specialized computation. The simplicity allows for easy programming using standard C++, but the programmer must be aware of the memory model. Now, coming to the data part and the pipelining part. The data part is intentionally simple. We are looking at a basic in order dual issue pipeline. Notice what is missing. There is no complex branch prediction, no speculative execution, and no out of order execution. Why this simplicity? Because these complex features, while boosting a single thread performance in a CPU, consumes a vast amount of power and silicon area. By eliminating them, the Epiphany gains predictable timing and high energy savings. The design pushes the burden of optimization onto the compiler and the programmer, forcing them to structure code that utilizes the dual issue capability effectively. Now, we will come to the memory hierarchy, the catchless software managed by the adaptive Epiphany. This slide highlights the Epiphany most radical feature, the catchless design. Traditionally, caches creates power-hungry complexity. Epiphany uses local scratchpad memory (SPM) on the each core for the low latency and the software manage, which ranges from 32 to 64 KB per core. It is flat distributed shared address space where every SPM is memory mapped globally for the direct remote access of it. The key concept of this slide is the adaptive epiphany is a con- is distributed shared memory model. Every core can address the memory of many core, but the programmer must use a dedicated DMA engine to manage data movement. In essence, the Epiphany replaces the complexity of hardware cache coherence with the predictability of explicit software controlled data movements. This is crucial trade-off for real-time systems. Now coming to specialized features and parallel scaling. First, talking about NOC, networks on chip. This 2D mesh is a high bandwidth and low latency, allowing thousands of cores to talk to each other very efficiently. Per core DMA. The DMA engine is another essential feature. It acts as a dedicated helper moving bulk data between local memories and external DRAMs, freeing the RISC cores to focus only on computation. Multi-chip scaling. The NOC and the E-links means this architecture is not just many on cores but truly scalable across multiple chips, supporting theoretical systems with thousands of cores. And it also gives you the highlights of a point true many core parallelism. Now coming to the last point, the historical significance and comparative takeaways from the adaptive epiphany. So the epiphany architecture is historically significant for demonstrating that kilo core chips are feasible outside of a research lab also. Its core legacy is proving that extreme energy efficiency is possible with radical architecture simplifications. Now, if we compare with the latest GPU in the market, the NVIDIA. While a GPU provides better raw throughput for a highly regular, embarrassingly parallel tasks, the Epiphany Mimid model and standard C++ programmability offered more flexibility for heterogeneous and irregular workloads. The Pella project was huge. By making this architecture accessible and open source, it inspired a generation of developers and research in embedding parallel computing. So this was all about the case study of the adaptive epiphany. I hope you loved I hope you get some information about the adaptive epiphany by this case study. Thank you.
So this is the program to calculate the factorial of a number, that is 8, for adaptive amphiphany. So this is our whole code, and now I will go for the step-by-step explanation of line by line explanation for the whole code. So we start with dot data. So basically dot data is a function which is used to, well, basically it is a function which is defined for the storage of the variables that remain same throughout the programs. So basically, we have defined two labels over here, start and end well. Okay. Basically, start and is assigned value 8. As we have to calculate the factorial of number 8 over here. So it will goes like 8 asterisk 7 asterisk 6 asterisk 5 till the value reaches the end well, that is assigned with the value 1. So we have written the statement and the dot word. Dot word is an assembly directive. Basically, it tells the assembler that we need a memory storage for 4 bytes, that is for integer, and the value we have to store in that space is 8. That the space name is start n, and the value to be stored in that 4-byte location is 8. The same is applicable for the end well, that we need a 4-byte storage. The name is endwell and the value stored in that is 1. So these are two, start n and end well. We have declared two labels over here, and the declares function is end from here. And when we write .txt, basically it tells us that the declaration function is end, and now there is a start of the code. So basically here we have defined our main method. We defined our main method over here, and basically as we all know that the processor talks in the language of registers. So we have loaded the values that is stored in the star n and the end will register and will memory locations to the registers S1 and register S2. Basically, now we'll use line valence again. Basically, it is the load address, the address of start n, basically, which is in the data, well, in the memory allocation area. So we will be storing the address of that particular storing that of that particular label to the S1, and now we will load the value of no, we will load the value at the particular address S1 in the register S1. So the value that will be stored in the particular register S1 will be 8. That is start in, the value of start in. Now S1 is equals to 8. The same we will be doing for the end well, and we will be storing the value of end well, that is 1 in the register S2. This is the same as I have told, load address. The address of S2 will be loaded at the address of end will be loading in the register S2, and then we will be loading the word, basically the things that are kept, the data that is kept on the register at the address of register S2 in the register S2 itself. Okay, so now our register S1 is loaded with the value 8 and the register S2 is loaded with the value 1. Now to perform a factorial of a number, we need a variable, basically a register, which as the processor uses registers. So we need a register that we have named S0, which will be containing the value 1. Basically, when we multiply the things, then we have to interfere the S0. When the loop will run, we have to interfere S0 again and again. So basically, if we take the value of S0 equal to 0, then the output will be wrong. So we have taken as the value will be 0 at the end, because something multiplied by 0 is 0. So we have declared the value of S0 as 1. So basically, we have used AD S0, comma X0, comma 1. Basically, it tells that S0 is equal to X0 plus 1. So X0 is a special type of register which contains the default value 0. So S0 will be declared as 1 because S0 is equal to 0 plus 1, that is equals to 1. So now we are going to the loop part, that is for 8, 7, 6, 5, 4 till the condition reaches false. So we are starting the loop from here. So we are using BLE S1 S2 and loop. Basically, branch is less than equals to S1. Basically, when the S1 value is less than equal to S2, the when the S1 value will be less than equal to S2, the loop will end. So now the value of S1 is now the value of S1 is 8 and the value of S2 is 1. So the 1 is not less than equal to 8. So it will go in S0, which is declared as 1. We have done over here. So S0 it is equals to 1. So S0 will be S0 asterisk S1, which is we now containing the value 8. So 1 asterisk 8 is equals to 8. So S0 will be currently will be having the value 8 in it. Then addition. We are using this command add S1 comma S2 minus 1 because there is no subtraction in the particular assembly language. So we are adding with the minus 1. We have to do the subtraction of minus 1 because if the value of S1 remains same throughout the program, that is 8, then the loop will be infinite and there will be no termination of loop that we have written the condition over here that BLE branch is less than equal to S1. The S1 will always be greater than equal to S2, that is 8. So the condition will always be false. So then again, the value of S1 is reduced by 1. So now the value, earlier the value was 8, now S1 equal to S1 minus 1, that is 8 minus 1, it will be 7. Then the condition will be it will jump to again back to this particular condition. It will check that S1 is less than equal to S2. If so, then end the loop, but the condition is false, so it will enter the loop. Then again it will go for multiply S0 comma S1 comma S2 basically. So now S0 is containing now basically S0 is containing the value 8 and S0 is containing 8 and asterisk S1 basically 8 asterisk 7 basically this is 56. So now S0 is having the value 56 and adding S1 comma minus 1. Again we are reducing the value of S1 by 1. So now the value goes 6. The loop will again check 6 is less than equal to 1 or not. If so, it will terminate and because as it is condition is false, it will again enter. Now the condition will be again checked that for the value of 5, then for 4, then for 3, then for 4, that's for 2, then for 1. As the value reaches 1, now S1 is less than equal to S1. So this is condition is true. It will exit the loop and it will come to this and jump loop. जैसे ये ऊपर जाएगा, it will exit the loop and it will come over here. So basically the factorial is stored in register S0 and now we will come over here. We will move the value of S0 in A0 register. So A0 is an argument register and now this is LI means load immediate A7 comma 1. A7 comma this statement is used for system calls. Basically A7 is a special purpose register which is used for system calls. That is we are using 1 that is for print of integer. That is we are using 10 for the exit of program. So li a comma 7 means the value it tells the means that it tells that we have to print the integer. Okay. So when we say e call to system call that is stored in a7 is invoked that we have to print the integer that is stored in a0. So the value will be printed that will be stored in a0. Then this program has not still ended because we have not done the end condition. So li a7 comma 10 basically it tells the assembler that we have to exit the program now. Basically 10 as I told you above that it is an instruction which is it is an register that loads the system call. So 10 stands for exit of program, or we can say end of program. So end of program will be stored in this, and as we call the call, the system call, that is stored in A7, that is 10, that stands for end of the program will be invoked and the program will be executed. And the value that was stored is already printed, and the result will be 4030. Now I will be showing you the drive or output for this. For this, you have to do the save the file and then assemble it, and now run it. The factorial of 8 is 40320, and we have successfully executed our program. Thank you.